Hello everyone. In this lecture we will discuss the infinitude of primes of the form 4n plus 3. We have by division algorithm every integer can be written in this form 4n plus r where r equal to 0, 1, 2 or 3. For example, if n equal to 0 then we have r equal to 0 means 0. So r equal to 1 means 1, r equal to 2 means 2, r equal to 3 that is 3. And if n is equal to 1 then we have 4 into 1 plus 0, that is when r equal to 0 means that is 4. So when n equal to 0 we obtained n equal to 0 implies we have applying these values we will get 0, 1, 2, 3. Okay, and if n is equal to 1 we have when applying r equal to 0, 1, 2, 3 we will get when n is equal to 1 that is 4 plus 0 that is 4. 4 plus 1 that is 5, 4 plus 2 that is 6, and 4 plus 3 that is 7. Then n equal to 2 implies we get 8, 9, 10, 11, etc. So every odd integer is of this form 4n plus 1 or 4n plus 3. That is we can express every integer in this form 4n, 4n plus 1, 4n plus 2, 4n plus 3 from this by using this. Okay, every integer can be expressed one of this form 4n, 4n plus 1, 4n plus 2, 4n plus 3. So we have this is even number and this is even. So we have every odd integer can be written in this form or in this form 4n plus 1 or 4n plus 3. For example, 13 can be expressed as in the form 4n plus 1 as 13 is equal to 4 into 3 plus 1. Okay, where n is equal to 3 here, and 25 also can be expressed in this form 4n plus 1 as 4 into 6 plus 1, that is n is equal to 6. Whereas 11 can be expressed in this form, 11 and 31 are expressed in this form, can be are in this form 4n plus 3 because 11 is equal to 4 into 2 plus 3 and 13 is equal to 4 into 7 plus 3. So every odd integer is of this form 4n plus 1 or 4n plus 3. Now we have a lemma. The product of any two integers of the form 4n plus 1 is also of the same form. That is, if we have any two integers which are of the form 4n plus 1, then their product is also of the same form 4n plus 1. Okay, that is the lemma. So the proof is simple here. Let a and b be any two integers of the form 4n plus 1. Then we have a can be written as some 4l plus 1 for some integer l, and b can be written as some 4m plus 1 for some integer m, because we have a and b are of this form 4n plus 1. So their product AB is equal to 4l plus 1 into 4m plus 1. So multiplying this we get 4l into 4m is 16lm. Then 4l into 1 that is 4l. Then 1 into 4m that is 4m. Then 1 into 1 that is 1. So from the first three terms we can take 4 outside. So 4 into 4lm plus l plus m plus 1. Now we have l, m are integers. So 4lm plus l plus m is also an integer, and let it be k. So it is nothing but 4k plus 1 where k equal to 4lm plus l plus m. It's also an integer. So AB is also in this form, the same form. Okay, 4n plus 1. Now this result can be extended to any finite number of such integers. That is, if we have a finite number of integers of the form 4n plus 1, then their product is also of the same form. Now we have a theorem. There are infinitely many primes of the form 4n plus 3. There are infinitely many primes of this form 4n plus 3. That is, we need to prove here. We can prove this theorem by contradiction. So if possible, suppose that there are only finitely many primes of the form 4n plus 3. We have to show that there are infinitely many primes of this form 4n plus 3. So if possible, suppose that there are finitely many primes of this form 4n plus 3, which are P0, P1, P2, etc., Pk, where P0 is the first odd prime of this form, that is 3. Now consider the positive integer n equal to 4 into P1, P2, etc., Pk plus 3. that is the product of these primes and 4, then plus 3. So that is n. Clearly we have n is greater than pk. Also n is of the same form, that is n is of this form 4n plus 3, because we have p1, p2, etc. pk. The product of these pi's will be an integer, so it is of this form 4n plus 3. Now we can consider first case. If n itself is a prime, if n itself is a prime, then n would be larger than the last prime pk. We have assumed that there are finitely many primes, and these are those primes. So pk will be the largest prime. Okay. So if n is a prime, we already obtained that n is greater than pk. So n will be a prime which is larger than this pk of this form, that is 4n plus 3, which is a contradiction, because from our assumption we have pk is the largest prime of this form 4n plus 3. So it is a contradiction. Now we can consider second case. If n is not a prime, if n is not a prime, then we have n is a composite. So if n is a composite, we have n is odd, because we have n has this form 4n plus 3. So n is odd. So since n is odd, every factor of n is of this form 4n plus 1 or 4n plus 3. If every factor of n is of the form 4n plus 1, then we have the by previous lemma n would be of the same form, that is the product of numbers of this form will be in the same form, that is the previous lemma. So if all the factors of n are this form, then we have n is actually the product of that factors. So n is also in this form. But we have n is of this form 4n plus 3 we obtained here. From this, n is of the form 4n plus 3. At least one of the prime factors, say p, must be of this form 4n plus 3. But since n has the form 4n plus 3, at least one of the prime factors has this form 4n plus 3. Let that prime factor be p. So p has the form 4n plus 3, and p is a prime factor of for n. Now we can consider a subcase. First subcase is, let p equal to p naught equal to 3. Okay, let p equal to, we have the primes of this form 4n plus 3 are p naught, p1, etc. pk. So if possible, suppose that p equal to this p naught, we know p naught equal to 3. Then in that case we have 3 divides 3. Also 3 divides n, because n is a p is a prime factor of n. So 3 divides n also. So since 3 divides 3 and 3 divides n, we have 3 divides n minus 3, that is 3 divides 3, 3 divides n implies 3 divides n minus 3 by the theorem 2.4. So n minus 3 is nothing, but we have n is equal to this 4 p1 p2 etc pk plus 3. So n minus 3 equal to 4 into p1 p2 etc pk. So 3 divides, from this we get 3 divides 4 into p1 p2 etc pk. So by the lemma 3.4 we discussed in the previous lecture, we have 3 divides 4 or 3 divides pi. We know if 3 divides p1 p2 etc pk, we have 3 divides pi for some I equal to 1 2 3 etc k. So since 3 divides this 2 into 2 into p1 p2 etc pk, we have either 3 divides 2 or 3 divides p1 or 3 divides p2 etc or 3 divides pk, which are not possible because 3 does not divide 2 and pi's are primes. So since pi are primes, 3 does not divide pi, that is 3 is not a 3 will not be a factor of pi's. So these are not possible. So this case is not true. Okay, now subcase 2, if p equal to pi were 1 less than or equal to I less than or equal to k, that means we know the primes of this form 4n plus 3 are p naught, p1 etc pk. So in the first subcase we suppose that this p is equal to this p naught. Now in second subcase we are supposing that if p equal to one of this pi where I from 1 to k, then we have p divides n, and already we know p divides n because n is of this form this, and at least one of the prime factor p has this form. So p is a prime factor of n. So we have p divides n and p divides 4 into P1 into P2 into etc. Pk, because we have P equal to Pi for some I from 1 to k. Therefore, P divides 4 into P1 into P2 into etc. Pk. So from the theorem 2.4 we have P divides n minus this. P divides n and P divides this. So we have P divides n minus this. So this is nothing but 3 because we have n equal to this. So P divides 3, which is again a contradiction because P is actually one of this P1, P2, etc. Pk. So both the cases lead us to a contradiction. So our assumption must be false. Our assumption was there are finitely many primes of the form 4n plus 3. So that is false. Therefore, we have there are infinitely many primes of the form 4n plus 3. Next, we have a note. There are infinitely many primes of the form 4n plus 1. There are infinitely many primes of the form 4n plus 1 also. Okay. Now we have a theorem, theorem 3.16, Dirichlet theorem. The proof of this theorem is not included in your syllabus. So the theorem states that if A and B are relatively prime, that is the GCD of A and B equal to 1, then the arithmetic sequence A plus B, A plus 2B, A plus 3B, etc. contains infinitely many primes. That is the arithmetic sequence A plus B, A plus 2B, A plus 3B, etc. contains infinitely many primes. That is the if A and B are relatively prime. That is the Dirichlet theorem. For example, we know 2 comma 3 is equal to 1, that is 2 and 3 are relatively prime. So we have, if you choose A as 2 and B as 3, we have this sequence is nothing but A equal to 2, then A plus B equal to 5, then A plus 2B equal to, that is we are adding 3, that is 8, 11, 14, etc. These sequence contains infinitely many primes. First prime is 2, second prime is 5, third prime is 11, etc. So we will get infinitely many primes if these A and B are relatively prime. That is the Dirichlet theorem.